Good morning, children. I think all you are safe at your homes and cautious also. Yesterday, we have given an introduction about electrostatics. In that, we have studied the properties of the charges. In the properties of the charges, we came across the attraction and repulsion force between the charges. We know that like charges are going to repel each other and unlike charges are going to attract each other. Now, we are going to learn with how much force they are going to attract with each other or with how much force they are going to repel each other. We have to find the magnitude. Suppose if two charges are being present at a distance, if you are going to take two charges at a distance, we have to calculate the force of attraction or repulsion depending upon the charges, with how much magnitude of force they are going to attract or with how much magnitude of force they are going to repel. So for that purpose, we are going to learn about Coulombs Law. This being similar to the law of what we have learned in your gravitation, that is in first year. So as two masses are being separated by a distance, there we have derived a formula like F is equals to Gmm by R square. And here also the same kind of law is going to repeat once again. That is, we are going to call it as inverse square law. Why? Because in that the force of attraction or repulsion is inversely proportional to square of the distance between the two charges here. So that's why it is going to call it as we are going to call it as inverse square law. Okay, so let us go with Coulombs law or Coulombs inverse square law here, and see what the Coulombs law tells about. The force of attraction or repulsion between any two-point stationary charges is directly proportional to the product of magnitude of two charges and is inversely proportional to square of the distance between them, and acts along. So what will be the force that is acting between the two charges? It acts along the line joining of two charges. Maybe the definition is going to be a little bit bigger. It seems to be bigger, but it's a very easy definition. We have to remember very few things here. We know that there might be a force of attraction or repulsion between two charges, and that force of attraction or repulsion is going to depend upon first factor is it going to depends upon the force of attraction or repulsion between any two-point stationary charges is directly proportional to product of magnitude of charges. See, look at this, product of magnitude of two charges. So this is the first important point where the force is going to depend on. And the next one is, and is inversely proportional to square of the distance between them. So here the force of attraction or repulsion is inversely proportional to square of the distance between the charges. And the third point is it acts along the line joining of the two charges. It acts along the line joining of two charges. So here in this particular definition there are only three important points. So the force of attraction or repulsion between any two-point charges. The first point is it depends on magnitude of the charges. How it depends on? Let us see. It depends on the product of, it is directly proportional to product of magnitude of two charges, first point, and is inversely proportional to square of the distance between them. This is the second point. How it is going to, the force of attraction or repulsion is going to depends upon the distance between them. This is the second point. And the third point is it acts along the line joining. So from this particular definition, we can able to derive a formula. Let us see that particular formula. It is very easy here. So now let us go with two charges Q1 and Q2 which are being separated by a distance R. They are being separated by a distance R. And now there might be a force of attraction or repulsion, we don't know that, but the magnitude of force between these two charges is directly proportional to product of magnitude of two charges. Product of magnitude of two charges, and is inversely proportional to, 1 by r square. 1 by r square means here it is inversely proportional to square of the distance between the two charges. So what is the distance between the two charges here? That is nothing but r. So now it is inversely proportional to square of the distance. We are going to take r square. So after writing these two equations, so from these two equations we can write directly F is equals to some k into q1 q2 by r square. Here k is called proportionality constant. So why? Because we are going to remove the proportionality symbol here. So then we have to introduce one proportionality constant, and later we are going to write the value of k also, experimental value of k here. So then finally we arrive with an equation F is equals to k into q1 q2 by r square. See these equations once again. F is directly proportional to q1 q2, F is directly proportional to 1 by r square, or F is inversely proportional to r square. So we are going to introduce a proportionality constant k here, and the value of k we can experimentally determine that the value of k is 9 into 10 to the power of 9 Newton meter square by Coulomb square. And here we have to observe this particular quantity epsilon naught. Why? Because k is equals to 1 by 4 pi epsilon naught. So epsilon naught is nothing but permittivity of free space. So every medium is going to have some permittivity, and it's a character of medium. For free space, its value is going to be 8.85 into 10 to the power of minus 12 Coulomb square by Newton meter square. Coulomb square by Newton meter square. Here the units are going to be important, here and here also, the value of k and for epsilon naught. So after all this, we can write an overall equation. From this we can able to write one equation. F is equals to 1 by 4 pi epsilon naught q1 q2 by r square. So this is what we call Coulombs law. After the derivation of inverse square law, Coulombs inverse square law, we can define Coulomb. That is nothing but the unit of charge. So here we will take the Coulombs inverse square law once again. Let us suppose if two identical charges, these are the two identical charges which are being separated by 1 meter distance. If they are being separated by 1 meter distance here in air or vacuum, if the force is going to be, if the force between the two charges is going to be F is equals to 9 into 10 to the power of 9 newtons, so then we can say that each charge carries 1 coulomb. Each charge carries 1 coulomb. I will repeat once again. If two identical charges are separated by distance of 1 meter in air or vacuum, and if the force of repulsion between the two charges is 9 into 10 to the power of 9 newtons, so then we can say that the magnitude of this charge is going to be 1 coulomb. And we can define it like this. Coulomb is that charge when placed at a distance of 1 meter from an identical charge in air or vacuum experience a repulsive force. Why? Because these are going to be two identical charges here. So then they have to experience a force how much here? 9 into 10 to the power of 9. So then the charge, the magnitude of that charge is said to be 1 coulomb. So we have to write the definition, and this definition is going to be important. We go with the limitations of Coulombs law. So here there are two limitations for Coulombs law. The first limitation is we can apply the Coulombs law for only point charges. Why? Because here if they are not going to be point charges, suppose here charge is being distributed on a body, and now if you want to find out the force between a similar body like this, let us go with another body here. On this we are going to have some more charge here, and this charge is going to be something like Q2, and this is going to be Q1. So then here we cannot able to find the actual force between these two charges here. Why? Because the charges are going to be spread all over the body, and different charges are going to be located at different distances from these two bodies. So then the force going to be, we cannot able to find the exact force between these two bodies. So hence thereby we have to understand that whenever if you want to apply the Coulombs law, definitely the two charges must be point charges. Suppose if this is a point charge Q1 and here this is going to be Q2, so then if they are being separated by a finite distance, so then we can able to find out the force between these two charges. So the first limitation is the charge must be points. So then only we can able to find out the force between the two point charges. And the second limitation is the charges must be stationary. The charges must be stationary. So now here they must be at rest. Suppose if they are going to move, always the distance between the charges is going to be changing. So thereby we cannot able to find the force between them. Why? Because F is inversely proportional to distance, square of the distance between them. So hence if the distance is changing continuously, we cannot able to find the force exactly. So here the charges must be stationary. The charges must be stationary. So then only we can able to find the force between the two charges. So here you might arrive with a doubt. So in your chemistry you came across with the atomic structure. In that atomic structure, as the electron is revolving around the nucleus, that electron is going to experience a Coulomb force of attraction, and there will be an attraction force between nucleus and electron. So here how we are going to apply the Coulombs law even the electron is revolving around the nucleus. So you might have that particular doubt. So in this case we have to understand that as long as the electron is revolving in a stationary orbit, there is no change in distance between the nucleus and electron. So always the distance remains constant. Here the distance between electron and the nucleus is always constant. So thereby we can able to apply the Coulomb's inverse square law for electron and as well as nucleus there. Okay. Right. The next concept is the vector form of Coulomb's law. So how we are going to write the Coulomb's law in terms of vectors? So for that purpose, here we are going to take two charges in the coordinate system, and from this origin from this reference point, these two charges are being located at a distances r1. That means we are going to represent the position of q1 with r1 vector. This is position vector of q1 is r1, and position vector of q2 is r2. And the distance between these two is something like r21 or r12. Later we are going to decide. So first of all, if you are going to take this particular position vectors, so this vector is going to be like this, and now the second vector is going to be like this, and the third vector is going to be like this here. So according to triangular law of vector addition, we can write, suppose if the vector is going to be from r21 is from that is from q1 to q2, so here this is the direction of r21. So in this case here, if you are not going to take this, as this is going to be the repulsion case here, I am going to make use of these arrows. So now r21 is going to be in this direction. So r1 plus r21 gives rise to r2 according to triangular law. So r1 plus r21 gives rise to r2 bar. So I required r21 here. So r21 is equals to r2 minus r1 bar. r2 bar minus r1 bar. And in coming up derivation, we required R21 cap here. R21 cap is nothing but here R21 bar by R21. So this is also the formula that we came across in your first year vectors lesson. So now let us go with the vector form of Coulombs law. General form is nothing but already we know that F is equals to 1 by 4 pi epsilon naught Q1 Q2 by square of the distance between these two charges. But in this case, here I am going to express the force on a charged particle F21 here. That will be equals to 1 by 4 pi epsilon naught Q1 Q2 by that vector between Q1 and Q2 is nothing but here R21 bar. So this is the distance what we have given there. Okay. So then in place of R21 we can able to substitute R2 minus R1. This is R2 bar minus R1 bar. In place of R21 we can able to substitute R2 bar minus R1 bar whole square, and this is in the direction of R21 cap. R21 cap. This is the unit vector along the direction of this particular vector. So I am going to make use of this vector. Why? Because this is the force and we have to make use of the direction of that particular force here. So then we can write F21 bar is equals to 1 by 4 pi epsilon naught Q1 Q2 by R2 minus R1 whole square into R21 cap. So already we know that R21 cap is, we can write R21 cap in terms of R21 bar by modulus of R21 bar. So now in this case this is R2 minus R1 is again now we can write R21 whole square, R21 whole square, and here if you are going to replace this R21 cap as R21 bar by R21 modulus of R21. So then this R21 whole square, modulus of R21 whole square and modulus of R21 here multiplied to get R21 whole cube, and left with R21 bar. So this is nothing but the vector which was drawn from Q1 to Q2 here. So finally the force between these two charges, the force on 2 because of 1, the force on charged particle 2 because of 1 is given by 1 by 4 pi epsilon naught Q1 Q2 by R21 whole cube, modulus of R21 whole cube, into here we are going to multiply with a vector. So this is R21. So this is the direction of that particular vector. And similarly we can find in the similar process we can able to find the force on charged particle 1 with respect to 2 also. Both are going to be in opposite direction and both are going to be equal in magnitude. So this is the vector form of Coulombs law. Okay, note it down. Okay. The next concept is force due to multiple charges. Suppose a charge is being surrounded by multiple charges. This particular charge is going to be surrounding with different charges here. We can take Q1, Q2, Q3, Q4, like that, Q5, like the different charges. So now we are going to calculate what is the net force acting on charge Q because of all these surrounding charges. So here, according to superposition theorem, we can able to find out the net charge, that is net force acting on this charge. So what this superposition theorem is going to tell. So the force acting on this particular charge is equal to the vector sum of all the individual charges. Vector sum of all the individual charges due to individual charges surrounding it. So first of all we have to find individual forces here. Let us suppose here the F1 is the individual force between Q and as well as Q1, and similarly F2 is the force between Q and as well as Q2, and F3 is the force between Q and as well as Q3. Like that, here if you are going to calculate the individual forces, they are going to act in this direction. That means here F1 is going to act away from Q, and here F2 is going to act away from Q2, and here F3 is going to act away from Q3. Why? Because these are all going to be the repulsive forces. So they are going to act away from these charges. So then we are going to indicate the forces in this direction. So then if you want to add all these sum vectorically, all these forces vectorically, so that will be the resultant force that is going to act on Q here. So then we can write F net equals to how much here? F1 bar plus F2 bar plus F3 bar plus F4 bar plus F5 bar. And this sum is vector sum. This sum is going to be the vector sum. We are going to add them vectorically so that we can able to find out the net charge, net force acting on this particular charge Q, which is present at point O. And now this can be written as simply we can write F bar is equals to sigma. This is summation of all the forces acting on this particular charge. So sigma F, and suppose if n charges are being located around this charge Q, so then we can be able to write the force F bar is equals to sigma Fn bar. Okay. Right. Now we will go with some important points about Coulomb force or electrostatic force. So these are being some important points we have to remember. Okay. While going with electrostatic force, it's a central force. What is the central force? So here central force means always the force has to act towards a point, and it has to depend upon the radius or something like I will give you one example. Suppose here there is a nucleus in atomic structure, and electron is going to revolve around this nucleus like this. So then there will be a force of attraction between these two charged particles, that means the nucleus and as well as the electron. Always the force will be towards the center here, towards the nucleus. So, and it depends upon the distance between the electron and as well as nucleus. So then it is said to be something like central force. So electrostatic force is going to be a central force. And next one is the force is conservative force. So this conservative force is also you have learnt in your first year while going with work energy power. So in that particular chapter, what is conservative force? So conservative force means here the work done because of this force is not going to depend on path followed by the charged particle or path followed by a particular object. So what is that here? If the work done by this particular force is not going to depend on the path followed by the particle, then it is said to be conservative force. Similarly, like gravitation force, here the electrostatic force is also conservative force. It is also not going to depend upon path where the work is being done. Okay, so here whatever be the path we choose, so the work done is going to be depends on the initial and as well as final points only. So that's why it is said to be conservative force. And next coming to the third point, it is going to form action-reaction pair. So here this force, once if you are going to create action and there will be reaction force, it also going to be developed according to that particular action. And now the fourth one is it depends upon the Coulomb's attraction force or repulsion force is going to depends on the medium that is being present in between the two charged particles. Suppose if the medium is getting changed, suppose if the two charged particles are being separated in air, so then we can have a particular force, and the same two charges are being separated, and in between them if some other medium is going to be present, so then the force is going to be something different. Okay, so here the force of attraction or repulsion is going to be depending on the medium that is being present in between the two charges. Okay, and the final point is here the force does not depend upon the presence of other charges. Other charges means here, suppose if group of charges are going to be present, or if one charge is being surrounded with a group of charges, so we have to calculate the individual forces. So now there is no interaction of other charge while calculating the force between any two charged particles here. So these are the few important points regarding Coulomb's force. Okay.